Let's take a look at a different Chinese battery pack as supplied with many of the generic tools. This one came with a new style of the handheld chainsaw with not only a safety button that you have to actually push the button in before you can actually pull the trigger and it will just pop back out afterwards. That's good. But it also comes with a little oil reservoir and a pump that you can squirt out oil onto the chain. That's very novel. However, we're looking at the battery. Because as with all these things, when a new product arrives, I tend to take the battery apart and just assess what it's like inside. There is a little spring goes on here, but it's loose. I'd left it out because I don't want it popping out, but it keeps the latch button up. And the first thing I noticed in this, I was looking at the tracks and where the connections to the batteries go, and it does have a battery management system, but if you look at this tap off the battery here, which is 2 cells away from this one, and if we actually zoom right down that, hold on, I'm just going to zoom on this. Let's see if this shows. Can you see that this tab overlaps the pad, and although it's got a layer of the solder resist over it, it really is just basically folded right over that. That's a bit squirmy, the fact it eclipses over that. Also, while we're zoomed down to this level, this connection here is the connection out to the tool, and it's supposed to be separated from the negative connection when these MOSFETs turn off. These are the ones that protect against over discharge. But the track actually passes right under this metal thing, and it is just relying again on the solder resist as a layer of insulation under there. I'm not so comfortable about that. Anyway, back down to the bench level we go, and we can explore the circuitry. This is different, incidentally. I thought this was just identical circuitry to the last one I looked at, but it is a different chip, and there's lots of extra components on here that they don't actually need, but they've put them on anyway, possibly just as a safety feature. They're playing safe because, you know, theoretically, if the chip went wrong, it could actually be quite a little inferno with all these cells connected to it. Anyway, let me show you the circuit board up close. So I'll focus down to that level and I shall zoom in just a little bit. I'll probably over zoom in. I do it so much. So this is a missing terminal here, which is quite odd. They have a slot for it. They have a position in the circuit board, and that is normally that is effectively common to the positive in here for this little jack plug for charging the cell. I wonder why they've left that off. Is it because this was designed to be plugged into? Because it is based on a Makita battery. Was it designed to plug into a Makita charger? And did they have issues with that, maybe with excessive current charging? Or I'm not really sure. But anyway, they've settled on just having the little jack charger. Where is the charger? One moment. No, I've misplaced it already. One moment, please. Ah yes, it just blended into all the other random black boxes. This is the charger and it says output 21 volts at 2 amps. It's not 2 amps. Besides, it weighs 60 grams or 2 ounces. It's so light that it just feels awkward. I'm going to open this in a separate video and we'll explore the circuitry. I roughly know what I'm going to see inside. Air mainly. But anyway, it's got the little jack that plugs into the battery to charge. That's it. It's quite a modular system. That's okay. There are a couple of diodes, and the positive of this is common to the positive of that. There's a couple of Schottky diodes. There's a MOSFET, a P-channel MOSFET that switches to the positive connection of the battery, which is common to this. There's the battery management chip, and there's a couple of MOSFETs that switch the output to the power tool from the negative connection of the battery here. And the reason for that is that they can turn it off under 2 circumstances. If there's a overvoltage situation across the MOSFETs, meaning there's a very high current being dropped across them, well, a high current passing through them causing a high voltage drop across them, it can detect that. I accidentally triggered that. It was quite interesting. But it can also kill power when the first of the cells around this pack reaches down to say about 3 volts. It will just kill power to the tool just to protect the battery pack from being over discharged. And likewise, when it's charging, this is the little MOSFET that will turn off when it reaches, the first of the cells reaches 4.2 volts. There is no balancing, just purely charge control. There is another little diode down here that is connected across the two tool outputs, just in case a sort of inductive loads cause a sort of transient voltage that could damage the MOSFETs. Anything else worth mentioning on here? One thing. Lots of tiny little capacitors. One bigger capacitor here, that's the one for the chip's power supply. Other than that, oh, also this little 8-pin array here, this position in the other chargers, it was a 8-pin MOSFET. In this case, they used an A19T, which is the P-channel partner to the A09T. And that's just basically, they've put in a dual footprint, which is quite neat. Under charging conditions, that barely gets warm. It's absolutely fine. Right, tell you what, let's take a look at the schematic. Or better still, let's take a look at the manufacturer's schematic for this. And it looks so simple because there's so little to it. But then they've added all these other components just to play safe. So what we have is the CW1053, and with this, it's super low pin count. Look at it drives the MOSFET directly with one pull-up resistor for the charging. It drives the output MOSFET directly. It's got a current sense resistor option, which they've not actually used, but they've done something else. And it's got a thermistor for monitoring the temperature of the battery pack. Little internal capacitor for voltage references, and then the cells just go straight to the chip. There's no resistor, but they've not done that. Let me show you what they've done. Quite interesting. They have treated it like the old traditional chips. Is everything visible here? Yes, it is. They've treated it like the previous version of the chip, and they've put a 1K resistor in series with each of the inputs and a little decoupling capacitor down to the 0-volt rail. And the reason they've done that is just to provide filtering. And I think they're also playing safe. It means that if the chip fails, those resistors are going to limit the peak current. There is the one resistor they've also added, and the larger capacitor there for providing power to the chip. Other oddities over here. Oh, they look like fuses, but it's just because I've drawn a resistor over an existing track. Other oddities, the pin 8 says no connection, but they've actually, because of the path of the circuit board and for space reasons, they've actually bridged that right through past that to the negative. So it is connected to negative. Sometimes the chip says NC no connection. Sometimes it is just no connection. Other times it's they say no connection for you, but the factory sometimes uses that as a control pin for a factory test function. So hopefully that's not the case with this. The data sheet is 2 sheets of paper. It's basically a rough spec in English, and then this pinout here, this layout. Anyway, the other things they've done, there is a double Schottky diode coming in from the charge pin. There's the charge socket, which is just common to that charge connection, and also to the pack negative. There's the diode that they've connected across the pack output. The MOSFET here, as well as having the pull-up resistor, should I say, that keeps that turned off normally. When this pulls down to presumably near the 0-volt rail, they've added a 3.3 megohm resistor. That also reduces the gate voltage, which is probably quite good, because typically you're aiming for 10 volts in the MOSFET. Except the logic level ones, which you're aiming for 2 volts or whatever you want, really. There is voltage sense. I think I triggered voltage sense. This 51K VM, I guess that means voltage monitoring in the output, and it will detect anomalies like perhaps the voltage increasing. There is also VINI, which is actually a current detection, and it is normally connected by this track down here to this sense resistor, but they've omitted that sense resistor, and they've taken that track with extra components directly over to the other side of the MOSFET, so it is measuring the voltage drop across the MOSFETs. And it's got a bit of filtering to allow for spikes when you pull the trigger on the tool and it causes a glitch of current, it will actually just allow it to, like a slow blow fuse almost, it's just going to slow the reaction to a short circuit. The temperature sensing, they have implemented it on the circuit board, but they've not put the thermistor in. So they've got it all tuned for a 10K thermistor, and then, let me show you this. Here are the pads that they'd normally have a thermistor soldered perhaps on the other side, just tucked down in between the cells to monitor the temperature. See this 10K resistor, 103, 10 and 3 zeros, 10,000 ohms. They've just tucked that across that. So they've got the option of either mounting a 10k resistor or just mounting this resistor, and that will make the circuitry think that the thermistor is at room temperature all the time, so it takes away that thermal protection. I guess they're just not expecting the tools to see too much duty. The MOSFETs are two GT90NO3D, just generic N-channel MOSFETs. Anything else worth mentioning here? Not really. It didn't take a huge amount of time to reverse engineer this, which is a refreshing change. Sometimes things like this do take a long time to reverse engineer, but I did have to get up to some trickery to be able to test how certain things were connected when I was actually testing this. And one of the things I did was I can show you that right now. One moment, I'll set it up and I'll show you it. So here's the setup. I've got a 1k resistor across the output to give it a very slight load, and that does get a little bit warm because it's got 19 volts across it, which means it's passing about 19 milliamps. The meter is hooked across the output there, showing 19.35 volts, and if I now bridge these two connections in the MOSFETs, the negative connection and the gate, it bypasses it and it turns it off. It does show a slight residual voltage, but it doesn't recover. The voltage doesn't come back afterwards. And this is because I've tricked it into, the chip thinks that it's turning those MOSFETs on, but it sees the voltage drop at the other side. And it just thinks that something terrible has happened, so it turns it off. So if I plug the charger in and the voltage goes up, it doesn't seem to turn the output on. It only turns it partially on for this for some reason. But if I then unplug that, it comes back up to its 19 volts again, and it's back to normal. I shall carefully not do what I did just earlier. Just in the last pause, I did actually bridge from here onto there, which is not a good thing to do because it's almost the other end of the battery pack. Yes, there was a bit of a spark. Exciting. It's been full of sparks and hot lithium cells recently. It's been an exciting time and nothing to do with this pack. But there we have it. It's a generic little pack. The circuitry is different. It's potentially much simpler circuitry, but they've added those extra components, which is good. The only things I don't like about it are, as mentioned before, the vicinity of this metal tab to that track, which is like 2 cells away. So that's about 8.4 volts potentially, and quite a lot of current if it ever went onto that. I'm guessing it would probably just blow the track clear. And this other one that is supposed to be switched by the MOSFETs, but it's actually passing directly underneath this metal clip that will probably move very slightly when tools are plugged in and out. I'd rather it had been routed differently so it didn't actually pass directly under that. But again, they've got a lot of current, haven't they? So they probably just thought, let's do it this way. And a bit of extra, they could have done what they sometimes do. They could have screen printed an extra block on top of that just as a layer of extra insulation. Likewise, they could have done that down here, but they probably weren't expecting maybe the tabs to be so big for some reason. The tabs shouldn't really be this size. They only need to be tiny ones, but they've used big ones. And they've also missed the tabs with the spot welding. They've just gone the very edge and splattered everywhere. But that's just what they've done. Oh, and it's also worth mentioning, there is a place for a third MOSFET to increase the current switching capability of the pack for higher power tools. And also that it lowers the voltage drop across the MOSFET, so it would allow higher current before the protection circuitry tripped. But it's interesting. It's very simple. It's very functional. It's not got the protection. Project Farm did a video recently about where he tested clones, good clones, unfortunately, ones that were fake, real batteries. But he tested them against the real ones, and the performance was very close, but they didn't have the protection against a dead short circuit. But these ones are just aimed at the cheapy Chinese tools, and for that, they're not actually too bad. The cells are supposedly, it says 1,500 milliamp hour. Whether it is 1,500 milliamp hour, I don't know. I could test that, couldn't I? But there we have it. The cheap chainsaw battery pack. It's actually not too bad, but it does have those little caveats, those little things that aren't quite 100% perfect. But other than that, not bad. Definitely, for the money, it's definitely not bad.